Hi, I'm Yatin Nandwani, and I'll be presenting the work done in collaboration with Deepanshu Jindal and under the guidance of Professor Mausam and Professor Parag Singla at the Indian Institute of Technology, Delhi. After excelling in perceptual tasks, neural networks are increasingly becoming popular for reasoning tasks as well. For example, solving puzzles like Sudoku and Queens, and without even knowing the rules of the game. Many decent architectures like neural logic machines, recurrent relational networks, or satisfiability net have been proposed to solve such reasoning tasks. While training, such architectures are shown many pairs of input puzzles and their corresponding solution, and the weights of the network try to encode the rules of the game implicitly by just looking at the solved examples. One issue that has been ignored till now while training such architectures is that of solution multiplicity. To demonstrate this issue, consider this simple Sudoku puzzle in which all but four cells are already filled. This simple puzzle has not just one, but two correct solutions, and finding any one of them would suffice. However, the state of the art RRN architecture has been trained only on puzzles that have a unique solution, completely ignoring solution multiplicity. As a result, such a pre-trained model achieves only 24% performance on such puzzles with more than one solution, while the performance on puzzles with a unique solution is whooping 96%. In this work, we address this issue of solution multiplicity while training models to solve combinatorial optimization problems like solving Sudoku puzzles. We first formally define the task of learning under solution multiplicity. We call it 1OML, one of many learning. We then present two naive solutions, naive loss and CC loss. Then we formulate the appropriate loss function for 1OML and propose two kinds of methods for optimizing the same. Meet greedy MinLoss and exploration based IExplore and SelectR. And finally, we look at the experimental results and some analysis. So formally, just like any other learning, we are given training data D as a bunch of training samples. But here, for each training input X, we are given a set of correct solutions, Yx. And the task is to learn a function f such that f of x is in this set of correct solutions. That is, f of x is any one of the many given solutions. Now the question is, how do we train such an f? What is an appropriate loss function for training f? Well, one naive way would be to compute the loss with respect to all the given solutions. So for example, in this case, we may compute the loss separately with respect to y1, y2, and y3, and then add. This clearly is suboptimal because even if the prediction is correct, let's say the prediction is y1, it still penalizes the model by computing the loss with respect to both y2 and y3, which will be non-zero. Another alternative is when the loss function is maximum likelihood. The alternative is to maximize the total probability of the target set yx. That is, in this case, we maximize log of probability of y1 plus probability of y2 plus probability of y3. And this gives us another loss function. We call this CC loss. But this also has issues for structured output spaces. And the main issue with naive loss and CC loss is that both of them treat all the target solutions as equally important, thus confusing the model. And this observation motivates our next loss function, LW. It picks only one of the correct solutions for training. Here in this equation, Wij indicates if the jth target has been picked for the ith data point or not. For each training instance xi, only one of the Wij is going to be 1 and rest all will be 0. Now the next question is, which target should be picked? Well, one simple strategy could be to pick the target for which the loss is minimum. We call this as min-loss. So for example, in this case, if let's say the current prediction corresponds to this star, so this is the model's current prediction. Now, the, the target Y3 is closest to it in the loss space, and hence min-loss would select Y3 for training the model. However, such a greedy strategy may also get stuck in local minima. A locally optimal choice for a particular data instance xi might not be good for the global optimization. To overcome this issue, we propose two exploration-based strategies, IXplore and SelectR. Instead of picking the target greedily, both select the other targets as well with non-zero probability. IXplore relies on the current probabilities assigned to different targets by the prediction model itself. On the other hand, SelectR uses an RL agent to select the appropriate target for training. We call such an RL agent in SelectR as selection module, which is parameterized by phi. The selection module takes the input X and the entire associated target set as input and returns one target Y. This target Y is used to compute the loss and train the prediction model. And based on the current state of the prediction model, the selection module gets a reward that is used for training its parameter phi. Intuitively, this reward captures how good the selected target is for training the prediction model. Finally, we evaluate different training techniques and losses on three different puzzles: N-Queens, Futushiki, and Sudoku. Base architecture for N-Queens and Futushiki is neural logic machines, whereas for Sudoku, we use state-of-the-art architecture, recurrent relational networks, RRNs. In this table, we look at the mean test accuracies, not only for the methods discussed above, but also for a bunch of other baselines as well. Amongst the baselines, we see that naive loss performs the worst, as expected, and our RL-based exploration techniques outperform not just the baseline, but other multiplicity-aware methods as well. Next, we look at the performance separately for the queries with multiple solutions, MS, and the queries with just unique solutions, OS. We see that SelectR improves the performance not only on MS, but also on OS. And this is true for at least two out of the three tasks. Next, in the Sudoku dataset, we know the number of solutions for a query may vary from 1 to 50. Now, this large variation in the size of the solution set allows us to assess its effect on the overall performance. So in this chart, on the x-axis, we have the number of solutions of a test query, and on the y-axis, we have the average performance over queries with similar number of solutions. We find that all models get worse as the number of solutions increase on the x-axis, but even though SelectR remains the most robust. Finally, all code and data is publicly available at this given link. Thanks.